All right. Hello, everyone. I am going to be giving a talk today called Good Enough for Now, Stability During R&D. For the purposes of this presentation, we're basically going to define stability as code which does what you want it to do and it doesn't have any bugs in it. We're going to ignore code that, doesn't do everything you want it to do because you haven't programmed it to do that yet, because we're talking about R&D, generally the phase of product development before you've released to the public, although we are going to be talking a little bit about the long-term effects that we've been experiencing from our decisions as we add features post-release. So who am I? My name is Amanda. Hello. I am one of the senior software engineers on the embedded team at Formlabs. So the embedded software team is responsible for the embedded code architecture on the 3D printers. We're not the only team that writes code for the printers, but we are responsible for the core architecture, maintaining it, building releases, stuff like that. As far as our product concerns go, the very most important thing for the 3D printers is that they have to be able to 3D print at absolute minimum in order for us to sell them and make any money. But on top of that, we also want them to be nice products to use. So we want them to look nice, be intuitive, tell you when something is wrong, and we want it integrated with our wider Formlabs ecosystem. So today we're going to be talking specifically about how this worked during Form 4 development. So basically, we have released the Form 4 relatively recently, springtime 2024. And ever since we started discussing it back in 2021, we knew we were going to do a very big rework of the software stack. For embedded, we'd use the same software for Form 2, we'd edited it to make it work for Form 3, and that was difficult enough. We were we cannot do this again for Form 4 because we want to do more complicated things. And overall, we decided that we'd gotten very tired of all our old tech debt, and that by building something from the ground up, we could have new and exciting tech debt. You will always have tech debt, but So who do we write code for? The embedded software has a lot of people as its stakeholders. So the hardware systems team is the team that is responsible for actually working on the science and engineering of how the 3D print runs. They're doing things like figuring out the right speeds to move your motors without splashing resin everywhere, how long to expose the resin for. And so they need basically a good hardware development platform to do their work in. They don't want to be software engineers. And then on top of that, we also have the product and the design teams who want to be able to add nice user-facing features. So the embedded team works basically for all of these people in order to enable their hopes and dreams. So before we get into Form 4, let's talk a little bit about what we did on Form 3 and what we really wanted to reset when we wrote our new stack from the ground up. So the Form 3 was basically using a state machine for all of the machine execution code. And this was great in many ways. It was always very easy to tell what your printer was doing. So for example, if you were lifting the build platform during the 3D print, I don't know how familiar you all are with the process of printing, you'd be oh, I am nested 5 state machines deep in the lifting state. And this meant that it was easy to debug, but whenever you wanted to change something, you had to connect it with all the adjacent states. So that was not very intuitive, it was kind of hard to read, and it was complicated for people who weren't on the software team to edit things. Also because it was a state machine and it really wanted to have only one state at a time, it was hard to do things like control loops. Our printer runs several control loops, one of which is keeping your resin at a good temperature, One of them is trying to make sure there's enough liquid resin on the SLA printers for you to print your next layer. And those don't express themselves very well in a state machine. The overall architecture. So this is the state machine I was just talking about. And this is our system for integrating with the wider Formlabs ecosystem. So over there are off-printer components. There's a web dashboard and there's the desktop software. These are all on-printer components. And because we kind of brought things up one at a time, everything talks to literally everything else. I have this little calculator here for all the things that calculate state. You can see that there are 3 places that get out of sync all the time. There is just Python on it, which would every so often just like eat up all your memory. So yeah, things were very fun and exciting. They were like extremely spaghetti code. And so in a nutshell, the pain points are like, it's difficult to add new hardware behavior in the state machine. Usually what this means in terms of like practicalities is that people will prototype new behavior in Python against a bunch of Python drivers, and then we either invest the time to move it into C++, or we leave it in Python and we just like keep it like running over the course of the print as a daemon. There's also like many different places where we assemble state. It's prone to like getting a little bit out of sync. It's like not intuitive, all the places you have to change. And there's like weird couplings between different applications because of when they were built. So like at some point, the firmware update required you to press confirm on the touch UI. And we've fixed this now, thank goodness. But there was a point where this meant that your firmware update depended on your touch screen working. And that also meant that if you had somehow broken your user interface, then like you wouldn't be able to update the firmware, which is like not the right scale of like mistakes and consequences. So when we went into Form 4, we looked at all of these pain points and we picked some specific goals. We wanted to make sure that hardware development was easy and that you could experiment against the production code so you wouldn't have that porting Python to C++ step. We wanted it to be easy to read and edit those files like with a text editor internally so that you would get better transparency in the system if you were like doing your R&D. And we wanted there to be consistent printer state across different ways of interfacing with the printer so that when you added a feature to one interface and product came up to you and was like, wow, that was really cool. Can we do that from the internet? Like, it would be a lot easier. And in a nutshell, here are the first 2 sets of requirements are basically based on enabling better internal hardware R&D, and the last of these requirements is based on enabling product and design to work faster and for features to be less expensive to add. So what does this mean in terms of like the actual software stack? Basically, we have some applications which we've been developing for like around a decade. I looked up like the first commit on like some of these repositories just for context. One of them's at like 10 years, one of them's at like 13. And so the web dashboard and the desktop software have to work with all of our existing products until we drop support for them. But basically, we want that interface to be very stable, very consistent. We don't want special handling for like each new device because we're going to have to maintain it for a very long time. On the other hand, the hardware that we develop for our 3D printers is going to vary vastly from generation to generation. We might be using completely different hardware processes. We might have a powder printer and a resin printer that we want to use basically the same interface, and like one of those prints versus using like specific wavelengths of light, and the other one uses like heat. Like they're completely different. So we want that to be very flexible in order to be able to use the same base framework and still accommodate vastly different things. We're going to be talking mostly on two major aspects of the Form 4 software. One of them is Orchestrator, and one of them is Task Engine. Task Engine is basically intended to enable the hardware team development, and Orchestrator is basically meant to enable like the feature development. Here is a rough diagram of what it looks like. Basically, you have the Task Engine talking directly to the microcontroller, and the only component that talks to Task Engine is Orchestrator, but Orchestrator is then responsible for talking to the TouchUI, the web dashboard, and Preform. This is basically a hardware abstraction layer, if you're familiar, but instead of the hardware it's abstracting basically the entire printer device. So yeah, what is Task Engine? So this was a huge part of the effort. It's what we call our new hardware layer. It takes instructions in the form of tasks. So they're like somewhat high level for a hardware interface. They're things like move motor and set LED. So these are kind of like process level tasks. And they make calls, they're wired through Task Engine basically directly to the MCU. We decided not to build a hardware abstraction layer inside of Task Engine. What this means is that if you want to run a test against a software mock of a motor, you can't do it. You're gonna have to test that manually. We basically decided this for speed reasons. An interface is like a lot of work. Hardware mocks, or like accurate hardware mocks, are like difficult to bring up because you have to make sure that whatever behavior you add in like hardware like is well modeled by your software. And even if you are using your software mocks for bugs, sometimes you won't fully catch the behavior because you're just not working in the physical world. You don't know what your edge cases are until you actually run your hardware. But because of that, it was like very easy during development to just like break other people's code. But like, it was kind of okay. So basically, when we were developing Form 4, all of the hardware development happened in one room in headquarters. This is headquarters in Somerville, Massachusetts. And despite the fact that we didn't have very good continuous integration, we didn't have like good software models for everything, we had a lot of hardware, and we had a lot of people who were printing like on the prototypes basically nonstop all the time. I think we probably had like 50 printers or something just going like day and night. And what that meant was that even though we didn't have like a good like continuous integration system in pure software, we were doing enough manual testing just by like everyone developing on the same stack, like on like constant internal releases, that generally we found our bugs pretty quickly. Even if we were finding them like after they merged, we would still find them pretty quickly. And if you broke someone else's code, you could just go over and knock on their desk and be like, "Hi, I am sorry. Can you explain to me what that was supposed to do? Because it's clearly not working anymore." Software is like very much about communication. So it's really important to understand like what other people built and why. And so a lot of the times that will take the form, it takes many different forms. Like on one end is like your code architecture and your APIs and stuff that's built directly into your code. And like on the other hand is like talking to people. And somewhere in the middle here is documentation, which is hard to find in Google Drive. And whatever form of communication you use is going to come with some trade-offs. It will take longer to build it into your APIs and architecture, but it will last longer. And it takes very little time to find things out by asking your coworkers face-to-face, but there will be no record of that information. If it's not discoverable, if it's not written down, if it only exists in the Slack messages between two people who no longer work at that company, then that image is going to be lost and is going to be basically the same as if like someone is going to have to relearn it. Another downside of the way we built Form 4 is that like very flexible, customizable system is basically like one size fits one. We were expecting that once we shipped Form 4, the hardware would be stable, and that meant that we basically accepted that a certain amount of like manual testing would get it to stability, and we would kind of stop there and not add a lot more features. And so we didn't really invest in a very extensive stability, like continuous integration system. What that has meant, though, is that like now whenever we add features, because we do want to add features, like a very recent example of this is the ability to just like drain a resin cartridge when you're not in the middle of a print. So if you have like 50 milliliters left in something, you can just empty it out and not get your hands dirty, like trying to like open the cartridge. And that was actually like weirdly complicated because the task engine had assumed that you would only ever dispense during a print. And so we kept running into weird bugs here that weren't written down, and we were like, why is this so complicated? And someone's like, well, we built it for this specific thing, and also the person who built it left for a different company. Good luck. But yeah, let's look at a different place where we made stability and flexibility trade-offs. So this is very far on the flexibility side. And Orchestrator is a lot more stable. So Orchestrator is the component I referred to as like a device abstraction layer. It's like another level up, and it lets you do things like upload logs, start a print, check for firmware updates. The orchestrator doesn't actually know very much about what the user interfaces look like. It doesn't care. It shouldn't have to. It basically accumulates all the state from Task Engine and serves it up to whoever is interested in it. For our very first version of Orchestrator, we knew it would be important to have APIs in place. But what that looked like at this point is that we had manually maintained JSON schema that we checked in beside the code. So if you added something new to the API, you were required and basically enforced just by the system of PR reviews to add a JSON schema so that other people would know what functions were available and what format those commands had to be in. And the trade-off of that was that it just took a little longer to build things than it did in Orchestrator in Task Engine. So whenever we added something to Orchestrator, it was like noticeably slower than adding functionality in Task Engine. In addition, because we had planned from the very beginning for Orchestrator to be reused in the way that Task Engine wasn't, you would generally have to make sure your code was general enough to use on multiple devices. And this meant that it was just like slower. And especially when we were trying to really hard to ship a new product, like there were often questions of like, oh, why is this taking so long? This was also a conscious decision we made though, because the people who worked on Orchestrator or developed against the API that Orchestrator provided were split kind of across several different places. So these stars, that one there is for headquarters. That's in Boston. This one here is a remote worker in Maryland. And over here, if I have aimed correctly, it should be Budapest. And so it's, and so basically that meant that communication just like took longer, and anytime you broke something and you tried to do remote debugging, where one half of that pair maybe doesn't have the most recent hardware, maybe you're working across a 5 or 6 hour time zone, it's much more difficult and it's much more expensive when you break things. So this is the software layout. Again, you've seen this before. And this is roughly the map of where everyone was based. By the time we were further into development, we had pulled people from like both continents into like most of the teams. But this is where like the owner of each component was based. So the concept of Conway's Law is basically that your organization produces code which is structured like the communication of your organization. So we have like teams for each application, and then there's like communications between them, which you can model more or less as the APIs. So for us, defining those APIs like serve to boost communication and like software stability, because every place where there is a gap, where you have to like transfer information between two teams, like you lose a lot of information. So defining those APIs well is very important. What are some of the downsides of this like relatively stable orchestrator approach? It is very expensive for us to make changes to this interface now because it's like touches so many different things. So the orchestrator code is used both on the Fuse Blast and the Form4 and the Form4L. And this means that if, for example, you wanted to move from manually maintaining your JSON schema all the time, I don't want to do that anymore, you have to do things like change 3 different interfaces, like at least for multiple different products. So like the scale of what you're doing is like much bigger. A lot of things like depend on that layer, and you're touching things that you're not super familiar with, or you're touching projects that people have like mostly moved off of because they're like not under active development, but you don't want to break them because they might be under development later. So you have to do a lot of work, often in like, for us, this means like multiple different languages, a few like user interface stacks and web stacks that the embedded team is not very familiar with. But since the embedded team is driving this migration, it means that a bunch of C++ developers are trying to figure out Go. So final thoughts. It would have been like, one of the things about making trade-offs is that there's a theoretical world where instead of choosing A or B, you got to choose A and B. But that's basically ignoring the constraint of time. You can always spend more time looking for more options. But when we built this tech stack, we were like, we are building this for a specific project to enable a specific project. So we need to get good enough to keep going, and then we have to just go for it. What this means is that there's a bunch of things where we're like, oh, we'll figure that out later. And that's a conscious like decision you can make. The important thing is that if you say you're going to think about it later, you like really have to spend some time and think about it later. Now that we've released Form 4, like we have a bit of time to look at what we've done and be like, okay, what was good enough for now? What was good enough to keep? And what do we really want to try and improve before we go through another cycle of product development? My team hears me say this a lot, but if you make something like easy to change on purpose, you make it easy to break by accident. If you make it like if you make it hard to break by accident, you're going to make it hard to change on purpose. You're going to end up with those trade-offs kind of like all across your stack. And eventually, you kind of want to move to a point where they're easy to change and hard to break. And you're just going to have to invest time into that. But overall advice, software is all about communication. So just pay attention to how people talk to each other, like places where you need to write things down, add stability by like recording things. Another thing is that if you don't have time to choose both flexibility and stability, you can prioritize different things on different teams. Making it so that Orchestrator was the only thing that talked to Task Engine meant that like the international teams could basically pretend that the Form 4 like printer software was a lot more stable than it actually was in headquarters. And probably kind of obvious, but like just after you've built something, take some time, reflect on what you would change, Maybe someday you too will get the exciting and kind of concerning project of rewriting your software from the ground up. Very fun, would not always recommend. And you're going to want to make sure that you're not repeating the same mistakes that you did before. But yeah, thank you for listening. We learned a lot from this process, and I hope you have learned something too from this presentation.